So in this lecture, in the next one, I will prove this theorem. The proof is divided into 2 lectures to have short lectures. We have seen in the previous one that in order to prove the theorem, it was enough to prove the Tilde Theorem. So that in the Tilde Theorem, we have an array of independent random variables which are uniformly negligible in this sense, and we have an extra condition that there exists a finite constant C for which A tilde and J is bounded by this probability for all J. And here is the definition of A tilde and J. I remind you, it's given by this integral, and what's the definition of Y? It's given by the lambda, the Poisson of parameter 1 transformation of the random variable x and j. So the theorem tilde reads as follows. Well, if there exists a sequence an for which this object converges in distribution to a random variable s, then this object converges to the same law. And if there exists an for which this object converges in distribution to a law s, then for the same sequence an, this one converges to the same law. So I'll divide the proof in several steps to make the proof very clear. And I'll start with step 1. Proof, step 1, or maybe step 0. Step 0, it's the following remark. Well, it's enough to prove that if I take phi as the characteristic function, if I take the characteristic function of phi of the sum in J of x and J tilde minus an of t, and subtract the distribution, the characteristic function of y tilde nj minus an of t, it's enough to prove that this difference converges to 0. I claim, so this is my step 0, I claim that in order to prove this theorem, it's enough to prove that this difference goes to 0. And why is that so? So let's prove the theorem, assuming that this condition holds. So the theorem reads as follows. Well, assume that there exists a sequence an, and this I want it to for all sequence an. For all sequence of real numbers, I want this difference to converge to 0. So assume that there exists 1 for which this expression converges to 0 in distribution to S. If this is true, we know that the characteristic function of this one converges to the characteristic function of that one for all t. So it follows from this condition that this characteristic function converges to fs of t. Now, since this difference converges to 0, it follows that this one also converges to fs of t. And by Lévy continuity theorem, it follows from this convergence for all t that this random variable converges in distribution to S. So that proves one direction. And the proof of second direction, it's similar. So indeed, if we want to prove this theorem, it's enough to prove that this expression converges to 0, whatever sequence an we choose, and we need this convergence to happen for all real number t. So in step 0, we proved that it's enough to show that this difference goes to 0 for all t and all sequence n. So now, in step 1, what I claim is that in order to prove that, it's enough to show that there exists a constant ct, which is finite, so that for all t, there exists a constant ct such that the sum from j1 to kn of phi x tilde n j of t minus 1, it's bounded by constant ct, and this for all t whose absolute value is bounded by t. So I claim in step 1 that if this holds, then this happens. So this is what I'm going to prove now. Well, So in order to prove that this converges to 0, well, I can also take the logarithm on both sides and say that the difference of the logarithms converges to 0. So it's enough, of course, that the log of phi, and I will not repeat here the long random variable, phi t, say x, just to remember that this is x, minus the log of phi, the sum of y's of t converge to 0. Right, so if I want to show that this difference converges to 0, it's enough to take the log here and the log here and show that the logarithms of this expression converge to 0. Now, what is the logarithm? Well, what is the characteristic function of this random variable? So let me write it here. If you have, let's say, x will stand for the sum minus an t, the characteristic function of x minus an when an it's a real number of t, this is just phi of x exponential minus I a t. So if I take the logarithm on both sides, that will be equal to the log of phi x t minus I a t. And you see that the minus at, which appears from the x, will cancel with the minus I an t, which will appear due to the y. So actually, I can just forget about this sequence an, and in this difference, it's enough to consider xn and yn here and there. Now, let me remind that the characteristic function of a sum of independent random variable, it's equal to the product, but we have a log, so that will give me a sum in j, and I will not write again that j runs from 1 to kn of phi x tilde n j t log, forgot the log, phi x tilde n j of t. So this is what remains from the first term. And now I have to remind the definition of y, which I erased. So remember that y tilde n j was the Poisson 1 transformation of x tilde n j, and that we have seen that the characteristic function of y tilde n j t was the exponential of the characteristic function of x and j tilde t minus 1. There was a factor here, lambda, multiplying this difference, but since lambda is equal to 1, it does not appear. So if we first remember that y are independent, so this is a product and therefore a sum. And now if we recall this identity, the log will cancel the exponential, and what will remain is this expression. So this is minus phi x n j tilde t minus 1. And now this expression, it's becoming very close to the one which we had to estimate in the proof of Lindbergh theorem. Because we have a log of phi x tilde minus this difference, we will use this assumption on the random variable, which guarantee, as I recalled in the previous lecture, that the supremum for all t less or equal than t, so that we know that for all t, so let me fix a capital T, for all t, the supremum for f x tilde n j t minus 1, that, well, this is converging to 0. So, and I forgot here the maximum in j. So I can fix a delta small, and I will conclude that this expression, it's bounded by a delta small, provided n is sufficiently large. So I will assume I'm taking n sufficiently large to have this estimates on the characteristic function of the random variable x tilde because they are uniformly negligible. And so that will allow me to rewrite this logarithm to do an expansion around 1. So rewrite this logarithm as logarithm of phi x tilde nj of t minus 1 minus f x tilde nj of t minus 1 and since this expression it's bounded in absolute value by delta, remember that if I have z bounded by a delta small, then the log of 1 plus z minus z, this difference, so there exists a constant which depends on delta, c delta, for which this is bounded by z square. So we know that this difference for all j and for all t bounded by a capital T which is fixed, this one, this difference is bounded by delta, therefore this difference, the absolute value of this difference is bounded by constant times z square. So I can apply this by taking this expression to be z. I have here log 1 plus z minus z, and I will conclude that the absolute value of this expression, so I'm taking here, I want to show that this expression it goes to 0, I'm taking its absolute value, this is equal to this absolute value. Now it's bounded by the sum of the absolute values, and the sum of the absolute values, it's bounded by phi x tilde nj of t minus 1 square. So if I want to prove that this difference goes to 0, it's enough to prove that this difference goes to 0. So if I want to prove that it goes to 0 uniformly in compact intervals, it's enough to prove that this one goes to 0 uniformly in compact intervals. And, well, we have seen how to manipulate such an expression. I will bound this sum of squares by the maximum in J of phi x n j tilde t minus 1 times the sum of J of phi x n j tilde t minus 1. So I know that the maximum converges to 0, right? This comes from this assumption. So this one converges to 0 uniformly in t. If we take the maximum for all t bounded less or equal than capital T, as n goes to infinity, that maximum will converge to 0. So if we are able to prove that the second one, it's bounded uniformly in n, so that there exists a constant ct for which this is bounded by ct, we will get that this is bounded by ct, this one converges to 0, and therefore this expression converges to 0, and that proves this convergence. So indeed, if we want to prove that this difference goes to 0, it's enough to prove the existence of a constant ct for which this sum is bounded by this constant ct. And this is our next goal. So in the previous step, we have seen that in order to prove the theorem, it's enough to show that for all t, there exists a finite constant ct, for which this sum is bounded by ct for all t with absolute value bounded by t. Now, my second step, my second claim, if you wish, is the following. Well, actually, it's enough to prove the following two results. The first one is that there exists a finite constant c such that the sum of the expectation of x n j tilde square times the characteristic, the indicator function of the set that x tilde n j it's bounded by 1, so that this is bounded by a constant C0. So there exists a C0 for which this is uniformly bounded by C0. So let's call that A. And B, we want to show that for all delta positive, there exists a finite constant C delta such that the sum for all j, that the probability that x n j tilde larger than delta, that this is bounded by C delta. So what I claim is that if you are able to prove A and B, then we can prove this step 1. We can prove that indeed there exists this constant. And this is what I'm going to do now. So I'll assume that I'm able to prove A and B, and I will deduce step 1. So this bound. So let's assume that. Let's fix T positive, and now I want to estimate this sum. So in this sum, I will just rewrite what is, and in terms of expectations instead of integrals, so this is expectation of exponential I t x n j tilde minus 1. So this is what I need to bound. And for that, I will divide this expectation in two pieces. The piece in which x n j tilde is larger than 1, and one in which is smaller than 1. So I introduce this indicator function. So this is a sum of two terms. And I will bound the sum by two sums. The first one is the expectation of exponential I t x tilde n j minus 1, the indicator that x tilde n j is larger than 1, plus the sum in j of the expectation of the same expression, but now x tilde n j it's less than 1. So let me consider first the first one and then the second one. And maybe I need some space, so at this point let me erase the statement of the theorem, and I'll consider first, I'll bound first this one, and then I'll bound the second one. So in this one, I will just bound this expression, put the absolute value inside the expectation. The absolute value of this difference, it's bounded by 2. So the first sum, it's bounded by 2 times the sum in J of the probability that x n j tilde it's larger or equal than 1. This is what we get for the first term, and now I can use B, to say, well, fine, let's apply that with delta equal to 1 to say that this is bounded by a constant. So this first term, it's bounded by a constant, and this is uniformly in n and uniformly in t because it doesn't depend on t. So this is how you estimate the first term. So now let's turn to the second one. For the second one, I will introduce itx and I will take it out. So the second one will be bounded by 2 terms. The first one, it's the expectation, the sum So I'm introducing here itx, so I'm subtracting and adding itx. So there is one piece which is the exponential of I t x n j tilde minus 1 minus I t x n j, and this on the set at which x tilde n j is bounded by 1. And then there is a second term, which is the sum of it x and j. And so this one, let me bound it by, so I have the absolute value of this term and the absolute value I. So I have t, but t, the absolute value of t, it's bounded by capital T. So I have a capital T here, and here I have x. But okay, the absolute value is still outside, so let me keep it outside. I'm sorry. Sorry about that. So I have the second term, which is expectation of it x n tilde times this characteristic function. It gets out of the expectation, I goes away, t, it's bounded by capital T, and what remains, it's x n j, the characteristic function of the indicator of the set that x and j, it's bounded by 1. Right? So let me go back again, because maybe you're confused. So here I had exponential it x and j minus 1 in the set in which x is bounded by 1. So I subtracted and I added itx. So here's the subtraction. I had a sum, but then I divided that in two pieces, two expectations. And in this expectation in which I have itx, I just moved out of the expectation and the absolute value, I and t. So I bound that term by these two pieces. And I have to show that these two pieces are bounded. Well, that's fine, because here I will use that the expectation of I theta or IZ minus 1 minus IZ, that this is bounded by a constant times z square, and this holds for all complex number z, to bound this term. So now I take the absolute value inside, I use that bound, and this first term, it's the first sum, it's bounded by j from 1 to kn. The expectation, there is a constant, and here appears t square x tilde n j square, the indicator that x n j tilde, it's bounded by 1. And now, well, this expression, so let me complete the bound of this expression. This one, it's bounded by constant t square, it's bounded by t square. And now we have a sum of x tilde square on the set in which x is bounded by 1, and this is bounded by c0. So I get a new constant here, c0 prime t square, due to a. So indeed, the first term, it's bounded by constant 0 times t square. So that's fine. So what remains to be estimated is this last term, and this last sum. We have, now what appeared here, it's the definition of a tilde nj. So this is why I didn't want the absolute value inside, because without the absolute value, this becomes a tilde nj. So this second term, it's equal to the sum j of a n j tilde. That's the definition of t, of a times t, of a tilde nj. So this is the second term. And now we have the bound which I alluded to and which explained why we replace x by x tilde, because for x tilde, we have this bound, that this is bounded by constant times t times the sum that the probability of x and j tilde is larger than 1/4. So you see, we can estimate this expression because we have this bound, that a and j, a tilde and j, is bounded by this probability. Because we will see that we are able to estimate this type of quantities, and by having this type of quantities, we are therefore able to estimate the sum of the a and j tilde. So this is bounded by the sum, and by condition B, this sum is bounded by C. So this argument shows that if A and B holds, then this statement holds, and therefore the theorem is proved. So in order to prove the theorem, what we really need to do is to prove these two bounds. And up to here, we used only assumptions on the sequence x and j. We never used the fact that x and j tilde, or y and j tilde minus an, were converging to something. So this assumption has not been used up to now, and therefore the proof of one statement or the converse statement will start by, it's enough to prove any of the two statements, it's enough to prove that these two bounds are valid, and this is where we are going to use this condition or that condition. So what remains to be done is to show that this condition implies these two claims, or this condition here, which is saying that the y and tilde minus an converging distribution to S implies these two conditions. So this is what remains to be done, and in this lecture I will just show that if this expression converges to S, then we have these two estimates. So here is the proposition I want to prove in order to complete one part of the proof of the theorem. I will assume that this sequence, for a sequence an of real numbers, is converging in distribution to some law S, and I will prove these two statements, and we have seen that once these two statements are proven, then we can show that also the sum of x tilde and j minus an converge in distribution to the same random variable, to the same law, and therefore with this proposition one part of the theorem will be proved. So let's prove this proposition, and the proposition will be proven in several steps. So the first step is that my claim is that if you fix t positive, then there is a constant c of t, which is finite, for which the sum from 1 to kn of the expectation of 1 minus the cosinus t x n g tilde, it's bounded by this constant t, and this uniformly for all t less or equal than t. So I claim that this estimate holds. So there exists a finite constant ct for which this is bounded for all t less or equal than t. And in order to prove that, well, let's start from our assumption. So we know that this happens. This means that the characteristic function of this variable converges to that one. So this means that phi of y n j tilde minus an of t converge to phi s of t, and this is uniformly in t less or equal than t. So say that we fix some t, and we know that, well, uniformly on that t, we have this convergence. Okay, but now what we will do is, well, let's write what is the characteristic function of this random variable. y, remember, it's the Poisson 1 transformation of x and j. So the characteristic function of this random variable, it's the sum, exponential of the sum of phi x n j tilde of t minus 1. So this is the characteristic function of that piece, minus I a n t, which is the characteristic function of this piece, and this is converging to fs t. Well, that means that if I take the log, I have, and before I take the log, let's do this observation. I know that fs of 0, it's 1, that fs, it's continuous, and therefore I can fix a t, 0, which is strictly positive, for which fs t minus 1, it's bounded by a delta, small delta, provided t it's less or equal than t0. So let me take t in this interval. So let me take the log on both sides. So that will tell me that this expression, it's converging uniformly in this interval. So here I'm taking the log, so that will disappear. Fx t t minus 1 minus I a n t, so that this is converging to log, and that I want to write it as 1 plus phi s of t minus 1, which is small. And this convergence is uniform, say for t less than t0. Now, let's phi s minus t minus 1, so this is bounded by z. So log of 1 plus z, the absolute value of that, it's bounded by some constant z, constant which depends on delta, if z it's less or equal than delta. And this by itself, it's also bounded by modulus of z, sorry, and this is bounded by a new constant c delta because z it's less or equal than delta. So this tells me that if z, the absolute value of z, it's bounded by delta, of course the absolute value of log 1 plus z, it's bounded also by a constant. So we chose t0 for this expression to be less than delta, so this means that if I take the absolute value of this expression, the absolute value converge to the absolute value. So now I'm taking values for t for which are bounded by t0, for which this happens, and this is bounded by a constant. So this means that, and since the convergence is uniform, what I have is that if I take the supremum in t less than t0, so here I'm using the fact that the convergence is uniform, and I'm uniform in this interval minus t0, t0. So the supremum of this expression, it's converging to that one, but that one, it's bounded, which means that if I take n sufficiently large, this supremum, it's bounded by a new constant c. So up to this point, we proved that there exists, due to this convergence, that there exists t0 such that, which can be small, but there exists a positive t0 for which this supremum, it's bounded by c, provided n it's very large. So now, if the absolute value of this expression is bounded by c, this means that the real part of this expression, it's also bounded by c. So let me take the real part of this expression, and what we get, well, here we get 0, and here, well, since this phi is bounded in absolute value by 1, this will give me that 1 minus phi, the real part of phi, it's bounded by c. So this means that there exists a constant c, which is finite, such that the sum of 1 minus the real part of phi x n j tilde t, it's bounded by a constant c0. And this holds for all t less or equal than t0. Right, so let me repeat. This absolute value, it's bounded by a constant. So this means that the absolute value of the real part, it's also bounded by the same constant. And what is the absolute value of the real part? Well, this is an imaginary, so we have the real part of this one, which is the real part of the characteristic function minus 1. If we take the absolute value of that, we get 1, because this one is bounded by 1, we get 1 minus the real part of phi x, the characteristic function of x tilde and jt. So this is what we proved so far. So let's continue and writing what is the characteristic function. So the characteristic function is the expectation of exponential I, x, and j. So if you want the real part, this will give me, so this is the expectation of 1 minus cosinus t x n j tilde minus 1. So this is bounded by a constant c0 for all t less or equal than t0. But I want that to hold for all t large. So this is exactly the estimated I want, but this estimate holds only for t smaller or equal than t0, and I want to extend it for all finite intervals. And the way in which we can do that is to recall that 1 minus cosinus 2s, it's bounded by 4 times 1 minus cosinus s. And by using this estimate, you see that you can go from the interval minus t0, t0, for which this holds, to an interval minus 2 times t0, t0. So this inequality allows us to go from the interval minus t0, t0 to the interval minus 2 t0 to t0, because if s takes value in this interval, we have this bound, but by this inequality, we can extend it to the interval minus 2 t0 to t0, paying a constant 4. So by iterating this argument, we can end by showing that there exists indeed a constant ct, which is finite, such that this sum, it's bounded by ct for all t whose absolute value is bounded by t. So we proved step 1 by using our assumption. So at this point, we can start proving these two statements. So let me prove the first one. So this is true. I fixed a t, capital T, and I know that this is true for all t between minus t and plus t. So let me just integrate this in t going from minus t to t and divide that by 2t. So from this inequality, we know that 1 divided by 2t, the integral from minus t to t of this sum, it's bounded by ct. So, well, we can, now this sum, it's a finite, so we can put the, this is bounded, so we can replace or place the integral inside the expectation and integrate it. And once we do that, we get that we have a sum of the expectation of 1 minus, And when we integrated minus cosinus, what we get is minus sinus of, so it's going tx, and this is divided by t, and this is bounded by constant t. Right, so this is, instead of integrating from minus t to t, we can integrate that from 0 to t by using the fact that cosinus is a pair function. Here we get the 2 out, so by integrating that from 0 to t, since sinus take value 0 at 0, we get that this is minus sinus at tx, and we have to divide that, which I forgot, so this is x and j, and this is x and j tilde. So this is what we get. Now, one first observation is that 1 minus sinus x divided by x, so that sinus x divided by x, it's always bounded by 1. So this is always positive. And also, if I take x larger than any epsilon, but here I will use that x is larger than 1, then this quantity, it's strictly positive. So 1 minus sinus x divided by x, it's strictly larger than a for x larger than 1. If the absolute value of x is larger than 1, then 1 minus sinus x divided by x is really larger or equal than a, which is a strictly positive constant. So I leave it to you to check this inequality, and I will use these two bounds to proceed. So first, I will say that this expectation, since it's positive and this is bounded by Ct, then if I take t x tilde nj, I want that larger than 1, of 1 minus sinus t x nj tilde divided by t x tilde nj, so that this is bounded by Ct. Right, because, well, this is positive, so here I'm introducing, so this expression is bounded by that one, and that one it's bounded by Ct, just because, well, this is positive, and I introduce 1, which is bounded by 1, a function which is bounded by 1. Now, if tx and j is larger than 1, I know that this is larger than a, so a times this sum it's bounded by this constant Ct. And therefore, what we proved is that the sum of the probability that x tilde nj is larger than 1 over t, that this is bounded by a constant which depends on t and which is divided by a. And this is exactly what we wanted to prove, because if you take 1 over t to be delta, you proved that for any delta, you have a constant which depends on delta, for which the sum of this probability is bounded by this constant which depends on delta. So indeed, if it follows from this estimate that B holds, that condition B holds. Now we will prove that condition A holds. Now it remains to prove the first condition from this statement. So here the proof will be not very different. We know that 1 minus cosinus x, it's always positive. So again, we are able to introduce an indicator. So since this is bounded by a constant which depends on t, the expectation of, let me take, since here we're taking x and j less or equal than 1, of 1 minus cosinus t x and j tilde. And this is bounded by constant t. Right? Since this 1 minus cosinus, it's positive, if I introduce this indicator function, it follows from this inequality that we have this bound. Now, we know that if A or Y, it's bounded, say, by 1/4 or 1A, let's say, then 1 minus cosinus Y, it's larger than a constant C0, which depends on A, so let's CA Y squared. Right, so if you look at small neighborhood of the origin, then 1 minus cosinus, it's bounded below by some constant times y squared. So I'm going to use this fact and the fact that x is bounded by 1, since x tilde nj it's less than 1. This means that t times x tilde nj it's bounded by t. So if I take t, so this holds for all t in this interval. So if I take t less than a, I get that 1 minus cosinus t x n j by this inequality, that this is bounded by a constant a t square x n j square. So this is telling me that since x tilde nj is bounded by 1, 1 minus cosinus is bounded below by constant t square. So what I get from this inequality is that constant t square sum of expectation x tilde nj less equal than 1 x tilde nj square, that this is bounded by this constant t. Here we can take, since these values are small, so t here, let's say it's equal to this a. Here we could have taken, to prove this first statement, t to be 1. That's fine. And so I'm taking here t, say, equal to a. So this means that this sum, it's bounded by this constant, which I said could be c1, t equal to 1, divided by a square times c0, where c0 is this constant which appears in ca. I'm sorry. So this is ca, which in where ca is this constant which appears in this inequality. So again, we have that this sum, it's bounded by a finite constant, and this is exactly what we wanted to prove here, that there exists a finite constant such that this sum is bounded by this constant. This is exactly what we proved here. So that completes the proof of the proposition, and therefore the proof of the main theorem of one direction, the proof of one direction of the main theorem. And notice that this assumption was used only to prove this estimate, and that this estimate, it follows from this estimate that we have these two bounds. And so in the next lecture, we will assume that instead of y tilde, we have the convergence of x tilde, and we will derive sufficient, well, we will have the other part of the proof, and but as I said, to keep this lecture not very long, I will leave that for another lecture.